Hey, welcome back to chemistry, and we're moving into a new chapter, chapter 5, which covers something called the stoichiometry of chemical reactions. So that is a word, and what does it mean? It doesn't mean really that much of anything truly exciting. All it really refers to is stoichiometry is a description of the quantitative relationships between reactants and products in a chemical equation. So let me just give you an example here. So let's say we are describing the reaction of sodium with chlorine gas to produce sodium chloride. And so we can write out a chemical equation as we've done. And so you can see that 2 moles of sodium will react with 1 mole of chlorine gas to give you 2 moles of sodium chloride. So one question you might be asked is, well, do we know what the stoichiometry of this reaction is? And the answer is, you betcha. The stoichiometry refers to the mole ratios in that chemical reaction. And the stoichiometry is that 2 moles of sodium, again, will react with 1 mole of chlorine gas to produce 2 moles of sodium chloride. So again, stoichiometry is basically a description of the mole ratios of a chemical reaction between the reactants and products, and it can be used to also understand the masses of the chemicals, or excuse me, the reactants and the products that are involved in the chemical reaction. Okay, so let me go over this one example. So what we have here is I have a chemical reaction that describes the combustion of a molecule called propane. So propane has the formula C3H8. There it's reacting with oxygen, and those 2 molecules will react and produce products. And one of the products is carbon dioxide and the other product is water. So as things now stand, what you may have noticed is that this really is not a balanced chemical equation. And so what we have to do is put coefficients in front such that for each of the elements we have as much atoms before the reaction as we do after the reaction. And so those are the numbers that you would need to put in. So we can basically see that 1 mole of propane, which is C3H8, reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. Now, if you wanted to, you could figure out what the masses of the reactants and the products are. And the way you would figure that out is just understanding what the molar mass of each of these molecules is. And so what you can do is you can figure out, for example, 1 mole of propane is 44 grams of propane. Or if you have 5 moles of oxygen, because each mole of oxygen is 32 grams, 5 moles of oxygen will be 160 grams of oxygen. And so 3 moles of carbon dioxide is going to be 132 grams of carbon dioxide, and 4 moles of water is going to be 72 grams of water. And what you'll notice is when you account for these mole ratios and the masses of the reactants and products, you will see that there is mass balance on either side of the equation, that there is as much mass before you have the chemical reaction as you do after the chemical reaction. In both cases, it's about 2 or 4 grams. Okay, so what we really need to do is sort of practice figuring out, if you know some values for the stoichiometry in a chemical reaction, can you calculate the other values? And so that will be represented on your test. So there are some problems I want to go over. So for the next 6 problems or so, what I want to do is write a word equation first, and then a balanced equation, and then answer the question that is asked in the problem. So let's go ahead and do problem number 1. So problem number 1, what we have is we have a chemical reaction where we have aluminum reacts with iodine to produce aluminum iodide. And then we are told how many moles of I2 are required to react with 0.429 moles of aluminum. Okay, so first off, let's write out a word equation that describes this reaction. So we have aluminum, and it's going to react with iodine, and we're going to get the compound that looks like aluminum iodide. So let me write that out, aluminum iodide. So one thing we have to do to get closer to the correct stoichiometric proportions of the reactants and the products is to write chemical formulas for each of these reactants and the product. So aluminum is an element which is monatomic in nature. Now iodine, you might recall, is one of those 7 elements. When it's a free element, it appears as 2 atoms stuck together. So we really should write I2 here. Now aluminum iodide is a compound, so you're going to have to figure out how many atoms of aluminum ions are stuck to iodide ions. And so there you're going to have to know the charges for these ions. So aluminum is 3 plus, iodine is minus, and so it looks like the formula here will be Ali3. Okay, so this is sort of an unbalanced equation which we need to balance. And so what I'm going to do is put in coefficients to make sure that for all the elements there are as many atoms of that element on the reactant side as the product side. So I'll try to do that really quick. So I think if I put a 3 here and a 2 there, then we have 6 iodines on either side of the equation. And so now I have to balance aluminum. So we have 2 aluminums on the product side. So I'm going to put a 2 on the reactant side, and so that seems to be balanced. Okay. So the question is, how many moles of iodine are required to react with 0.429 moles of aluminum? Okay. So that's not too hard to figure out because we are given in this balanced equation a proportion of how many moles of aluminum react with how many moles of iodine. So I will write 2 moles of aluminum will react with 3 moles of iodine. And so that actually is an equality for that problem. We can say that 2 moles of aluminum is equal to 3 moles of iodine in this problem. And so we could write out a couple fractions. So I'll just write 1, for example. I don't know if we're going to use this to solve the problem. We can write 2 moles of aluminum over 3 moles of iodine. Okay, so now we're at, in the problem, 0.429 moles of aluminum, and we want to get this into moles of iodine. And so the question is, do we use this fraction or the reverse of it to convert moles of aluminum to moles of iodine? And it looks like we're going to need the reverse, right? So it's going to be times 3 moles of iodine over 2 moles of aluminum, and the moles of aluminum cancel, and you get an answer in moles of iodine. So the math would be 0.429 times 3, so it should end up 0.644 moles of I2. Okay, so let's go ahead and do another one. Okay, sodium reacts with oxygen gas to produce sodium oxide. If 2.5 moles of sodium oxide were produced in the reaction, how many moles of sodium and oxygen gas were used? Okay, so first off, we need to write out a word equation to describe this reaction. So we have sodium metal, so I'm just going to write sodium. And it's going to react with oxygen gas. And we're going to produce the compound sodium oxide. Okay, so sodium, again, is monatomic in nature when it's an element. Oxygen is one of the 7, so it should be diatomic. And then sodium oxide is a compound, so you're going to have to figure out the formula. It's an ionic compound, much like aluminum iodide was in the last question. So sodium is Na plus, oxygen in the ion state is O2 minus. So it looks like the formula is going to be Na2O. So now we need to balance this equation. So it looks like we have 2 oxygens on the left, 1 oxygen on the right. I'll put a tier, so that balances the oxygens. We have 4 sodiums on the right, only 1 on the left, so I'm going to put a 4 here. So we're starting out with, it looks like 2.50 moles of sodium oxide. And what we're going to have to do is get this into moles sodium that were used in the reaction first. So that's actually not too hard to figure out because, again, what we see is a mole proportion between sodium oxide and sodium. And so what we can see is that for every 4 moles of sodium that react, we get 2 moles of sodium oxide. So what we can do is just throw in this 4 mole of sodium over 2 mole of sodium oxide. And so, whoops, there we go. Okay, so the sodium oxide, moles of sodium oxide cancel, and you get an answer in moles sodium, and so it'd be 2.5 times 4 divided by 2, so I'm guessing it's going to be 5 moles of sodium. So you do something similar to figure out how many moles of oxygen would be used in this reaction. So again, it's 2.50 moles of sodium oxide that were given, and this time we have to figure out how many moles of oxygen were used to produce that amount of sodium oxide. And so here you can see that for every 1 mole of oxygen gas, you get 2 moles of sodium oxide. So here it'd be times 1 mole of oxygen gas over 2 mole of sodium oxide. Moles of sodium oxide cancel. So it looks like the answer should be 1.25 moles of oxygen. Okay, so we move on. Okay. So with question 3, it is what are the number of moles and the mass of chlorine gas required to react with 10 grams of sodium metal to produce sodium chloride? Okay, so again, let's start out with a word equation, write a formula equation, balance, and then try to solve the problem. So it looks like we have, it says a number of moles, a mass of chlorine required to react with 10 grams of sodium metal. So we have sodium metal again, plus chlorine gas. And are we getting sodium chloride? Yeah, it looks like we are. So it's just a synthesis reaction of sodium chloride. Okay. So again, let's write out the symbols. So sodium is Na. Chlorine is one of these elements that will be diatomic in the elemental state. And I think you all know what the formula of sodium chloride is. It's going to be NaCl. Okay, so now we need to balance it. 2 chlorines on the left, 1 on the right. I'll put a 2 there. And then to balance sodiums, we need a 2 there. So we're trying to figure out the moles and the mass of the chlorine gas required to react with 10 grams of sodium metal. So we're really starting out not with moles of sodium metal, but now we're starting out with grams of sodium metal. So we have 10.0 grams of sodium. Now, we cannot say, for example, that the ratio here between sodium and chlorine is 2 grams of sodium and 1 gram of chlorine gas. We cannot say that because these numbers in front are not mass ratios. We can say, however, that 2 moles of sodium will react with 1 mole of chlorine. So our goal at this point is we want to use this proportion between sodium and chlorine because then we can get an answer in chlorine. But first, we have to convert the grams of sodium to moles of sodium. So we have to really work that out. So here we just use the molar mass of sodium, which is in the periodic table I have there. So it's times 1 mole of sodium over 22.990 grams of sodium. So the grams of sodium cancels out and we get an answer in moles of sodium. So we're at that point now. So now we want the moles and mass of chlorine. So we can at least next calculate what the moles of chlorine are because we know that for every 1 mole of chlorine produced, you need 2 moles of sodium. So the moles of sodium cancel out and we get an answer in moles chlorine. So you can work out what the moles of chlorine would be at this point. It would be 10 times 1 times 1 divided by 22.99 divided by 2. And so the answer there should be 0.217 moles if we were to work out moles chlorine. But let's go ahead and get this to grams chlorine. So what we have to do is take moles chlorine to grams chlorine. And so we need to know what the molar mass of chlorine gas is. And so 1 chlorine atom has an atomic mass of 35.45. But how about 2 chlorine atoms? So if you had 2 chlorine atoms, that would be 35.45 times 2. So I think that's going to be 70.90 AMU, which for chlorine. So that means 1 mole of chlorine is going to have a mass of 70.90 grams of chlorine. And so what you can do is you can use that proportion and put it into this equation. So let me actually, I'm going to have to erase that to give myself a little bit more room. Okay, so we'll just move it down here. So we have 70.90 grams of chlorine over 1 mole of chlorine. And it looks like the moles of chlorine cancel. And so we get an answer in grams chlorine. So you should be able to take 10 times 70.90 divided by 22.99 divided by 2, and I'm hoping you'll get 15.4 grams of chlorine. So that should work out. Okay, let's move on to the next problem. Okay, mercury oxide decomposes into mercury and oxygen gas. What are the number of moles and the mass of oxygen formed by the decomposition of 1.252 grams of mercury oxide? Okay, so let me write out an equation here. Here we have mercury, and we're told what the charge is, which helps. Oxide gives you mercury plus oxygen gas. So let's write out a balanced equation. So mercury oxide, mercury is going to be 2 plus, oxide is 2 minus, so it's HgO should be the formula for mercury oxide. Gives us mercury metal, which is monatomic in the elemental state, and oxygen is diatomic in the elemental state. So let's balance this, 2 oxygen here, 1 here, and so I think it's now balanced. Okay, what are the number of moles and the mass of oxygen formed by the decomposition of 1.252 grams of mercury oxide? So we have 1.252 grams of mercury oxide. Now we want to get this into moles and mass of oxygen. So again, what you can see here is that when we have these proportions here, these coefficients in this equation, again, these are not mass coefficients, these are mole coefficients, and so we can see that for every 2 moles of mercury oxide we get 1 mole of oxygen gas. So what we really need to do is take the grams of mercury oxide and get this into moles of mercury oxide. So there, what we need to do is we need to know the molar mass of mercury oxide. So it looks like we have, I'll write this down here, it looks like we have, so the molar mass of mercury oxide is going to be equal to 200.59, which is the molar, or excuse me, the atomic mass of mercury, and then 15.999 for oxygen. So let me get my calculator out and figure out what that is. So it's going to be 200 plus 15. So I get 216.589. So that tells me that 1 mole of mercury oxide should have a mass of 216.589 grams. So I'll write that here, times 1 mole of mercury oxide over 216.589 grams mercury oxide. So grams of mercury oxide cancel, we get an answer in moles of mercury oxide, but again, we need to get this into oxygen. So now we can use the proportions here of 2 mercury oxide to 1 oxygen, because that refers to moles. So I'm going to write here 1 mole of oxygen over 2 mole of mercury oxide, and the moles of mercury oxide cancel. Now we're at an answer at moles oxygen, and so that's one thing we want, but we also want to have the mass of oxygen. And so I just kind of know at this point the molar mass of diatomic oxygen, well, 1 atom is 16 for oxygen. If you have 2 atoms, it'll be 32.00 mu, so that means 1 mole of O2 will have 32.00 grams. So I'll just write that here, 32.00 grams of oxygen over 1 mole of oxygen. Okay. So anyway, if you did this entire equation, that would give you the mass of oxygen in the problem. So it's 1.252 times 32.00 divided by 216.589 divided by 2. So hopefully that should work out to what that number is on the screen, which is 9.248 times 10 to the negative 2 grams of oxygen. Okay, let's move on. Okay, next problem. It get a little bit more difficult. Okay, what is the number of moles and mass of copper carbonate needed to produce 1.5 kilograms of copper oxide? And CO2 is the other product of this reaction. Okay, so we have copper carbonate. So let me write that out. Let's see what we have here. We have copper to carbonate. And it looks like it's being decomposed into copper to oxide. And then the other product is carbon dioxide. Okay, so copper to carbonate. So, well, we have copper is 2 plus, carbonate is CO3 2 minus. This is an ionic compound, so we should have CuCO3 should be the formula. Copper oxide, again, we know Cu is 2 plus, oxide is 2 minus, so the formula is CuO. And then carbon dioxide is that. Okay, let's just check to make sure that the equation is balanced. It looks like it is. One carbon atom here, one carbon atom here, one carbon on the left, one carbon on the right, 3 oxygens on the left. Looks like a total of 3 oxygens on the right. So that helps. So that makes it a balanced equation. Okay, so now what we're trying to figure out is the moles and the mass of copper carbonate, this stuff here, need to produce 1.5 kilograms of copper oxide. So we have 1.50 kilograms of copper oxide. And so we have to take going from copper oxide basically over into copper carbonate. And so what you have to do, again, is if you are starting out with mass, we'll have to convert this to moles, because the only way we can convert copper oxide to copper carbonate is by using the mole ratio of 1 mole of copper oxide is produced from 1 mole of copper carbonate. So we have to get copper oxide into moles. So we have 1.5 kilograms of copper oxide. Okay, we'll have to use a molar mass, and you might remember that a molar mass is the number of grams in 1 mole, but we have kilograms here. So we'll have to first basically get kilograms into grams. So it's going to be times 1,000 grams of copper oxide over 1 kilogram of copper oxide. So here, kilograms of copper oxide cancel out, and we're now at grams of copper oxide. So now we have to get this into moles of copper oxide using the molar mass, which fortunately we're given. So it's 79, let me redo that. There we go. So it's times 1 mole copper oxide over, looks like it's going to be 79.54 grams of copper oxide. And the grams of copper oxide cancel, we get an answer in moles of copper oxide. And then where we're going with that is we're at copper oxide now. Now we can go to copper carbonate. And you will note that, again, 1 mole of copper oxide is produced for every 1 mole of copper carbonate. So we know 1 mole of copper carbonate here. Let's get this into, copper oxide. Let's get this into copper carbonate. So it's going to be times 1 mole of copper carbonate over 1 mole of copper oxide. So the moles of copper oxide cancel out. We get a mole of copper carbonate. And then the last thing we need to do is get this into grams of copper carbonate. And then I guess we maybe even want kilograms. So it's, let's see. We have a molar mass of copper carbonate, which is 123.55 grams of copper carbonate over 1 mole of copper carbonate. So now we're at grams of copper carbonate, and we wanted to, we could convert this to kilograms. So that would be what? 1 kilogram of copper carbonate over 1,000 grams of copper carbonate. So grams copper carbonate cancels. So we have an answer in kilograms copper carbonate. So you can work out the math, but what I'm hoping is you'll find that the answer should be as stated, which is 2.330 kilograms of copper carbonate. Okay, so let's move on. Last problem. The last one's a little weird, but actually it's not too difficult to solve once you sort of kind of figure out what to do. Okay, so we're given an equation here. I need to bring that up. Okay, so let me just first write that equation on the board. So we have potassium iodide plus silver nitrate. I'm going to leave out the state symbols just to make my life easier. And we have potassium nitrate and silver iodide. Okay, so the first thing I want to do is make sure the equation is balanced. And just looking at it, looks for each element we have one atom on either side of the equation, except for oxygen, which has 3 on either side of the equation. So that equation looks balanced. So the problem is we have 25 milliliters of a 0.5 molar potassium iodide solution, and they're adding excess silver nitrate salt to make the precipitate here silver iodide. How many grams of silver iodide are formed? Okay, so here's the problem. So normally, we know that eventually what we want to do is we want to get this into grams of silver iodide, right? And so that wouldn't be so bad. We can convert, maybe before that, we'll have moles of silver iodide. We convert that to grams of silver iodide using the Mohr mass. So if we have the moles of silver iodide, then we can figure out how many moles of potassium iodide we need. Because you can see that for every mole of potassium iodide, you get 1 mole silver iodide produced. So we can easily convert that to moles of potassium iodide, but here's the problem. We're not given moles of potassium iodide or the mass of potassium iodide in the problem. We're given some other information. So the question I might ask is, maybe from that other information, maybe we can figure out what either the mass of potassium iodide is or the moles of potassium iodide is. So let's see where that other information takes us. So we have 25.00 milliliters of a 0.500 molar potassium iodide solution. Okay, so molar. So let's look at that just for a second. So you might remember molarity, capital M is equal to moles divided by liters. Okay, and so my question is, can we figure out moles of potassium iodide? And so let's see, let's just solve this equation for moles. So we have moles of potassium iodide is equal to molarity times liters. So the question is, do we know molarity and do we know a volume in liters? We do know molarity, and we can take this volume in milliliters and convert it to liters. So yes, we can get a moles of potassium iodide. So that makes life pretty simple. Okay, so what I'm going to do is I'm going to kind of set this up in a slightly different way. Just to try to show you different ways of solving these problems. But again, we can easily get moles of potassium iodide simply by multiplying the molarity of potassium iodide times the volume in liters. So let me set that up. So let's just do by factor label. So I'm going to write over here, we have the molarity of potassium iodide, which is 0.500, and it's capital M, but you know that molarity is equal to moles divided by liters. So I'm going to write that out. I'm going to write 0.500 moles over liter. Now, we have 25 milliliters here. So let me go ahead and write that in, and I know that we can't balance the units, but let's see if we can mess around with that and see what happens. So it's going to be 25.00 milliliters. I'm just going to leave it like that. So the question is, can I mess with this and convert this into liters? And I think I probably can. So it's going to be times 1 liter over 1,000 milliliters. Now let's see where we're at. Let's see what cancels out. Okay, so we have a liters here, which cancels out. We have milliliters here, which cancels out. So we should have an answer in moles. And we notice we added 25 mils. That's perfectly fine. It doesn't have to be in a fractional form. What you really have to look out for is when you're solving the equation that the units that they need to cancel do cancel. And it looks like they do. So basically, we're at a good point here. We're at 0.5 moles of potassium iodide. And so can we solve the rest of the problem? And I think we can. So you can see that for 0.5 moles of potassium iodide, we can get this into moles of silver iodide. So I'm going to write times 1 mole of silver iodide over 1 mole of potassium iodide. And so moles potassium iodide cancel, we get an answer in moles silver iodide. And then the final step is we want a mass of silver iodide. And I think we're given the molar mass, thank goodness, in the problem for silver iodide, which is 234.77 grams of silver iodide over 1 mole of silver iodide. So the moles of silver iodide cancel. So we should get an answer in grams of silver iodide. So the math would be 0.5 times 25 times 1 times 1 times 234.77 divided by 1,000 divided by 1 divided by 1. So I think in the answer you would get this number, 2.93 grams of silver iodide. And it should be rounded to 3 significant figures because we're limited here to 3 significant figures. Okay, well thank you for listening and we'll see you next time.